Good morning, Patrick.
Good morning. Hey.
How are you?
I'm fine. How are you?
Good, good. Do you have a paper for us?
I guess I've got a paper for you. It would be so embarrassing if I now say no.
Sorry, I'm getting an echo, but where is it coming from? Here we go. Voila, that's turned up. Great. Do you want to share the link already so I can put it over on YouTube as well?
Yeah, sure.
Fantastic. Good morning, Valentina. Since Zoom has this new blur feature, everyone is sitting in the same house. Look at Evie showing off his nice 3D printed brain. All right, we just wait one more minute. And then we can start.
Hello.
Hey, Hervé.
Hello.
Hey, Pat, hey, Valentina, hey, Stephanie. How are you doing?
Now, you kind of primed that question, but what instrument do you play, Evie?
Okay, I'm coming back.
Are we getting a live jingle now?
That would be amazing.
I'm a little bit scared of what's going to come now. Seve, you never know what you get. Good morning. Ooh.
Good morning.
Oh my God, that's so cool.
Yeah. Can you actually play it, or does it just look cool?
I'm not gonna play. I need to put stuff here, stuff like. It's Monday morning. Cannot do it.
Fair enough. Well, I see you again on Tuesday, Wednesday, and Thursday. Let's see if you can do it then.
But it was a good try to get a jingle out of him that you can use for the Neuroccino.
Well, for Neuroccino, we already have a jingle.
Do we?
What? What is a jingle?
You guys.
You've never seen the replay on YouTube?
Oh.
So we now have a little bit of music in the beginning of Neuroccino, the jingle. But we're still looking for some nice music for CNS talks and things like that.
Okay.
And I'm looking at you, Eric.
I'm not here.
Fantastic. Right, let's make a start. Thanks for joining us this morning. Welcome to Neuroccino, everyone. The way it works is anyone is welcome to just come along and present a paper or a book or a chapter that they got interested. It's too early. That they got interested in, and tell us why you like the paper, why it's cool, why we should be reading it, and we just discuss it. Today we have Patrick, who is presenting for us. So Patrick, you know the drill. Take it away. Just share your screen.
Alrighty.
Thank you.
So I guess you can see the screen now, right? Is it visible?
Yes.
Good. Okay. So today, I'd like to showcase this study by, I'm going to butcher the name, and I'm sorry for that, but by Tirso René del Jesus González Alam, who investigated hemispheric differences in the cortical networks along the principal gradient. So in case someone is unfamiliar with the term principal gradient, I just quickly show you this picture by the highly cited paper by Daniel Margulis, 2016 PNAS, where he and colleagues used resting state functional connectivity across surface areas and embedded them into a lower dimensional space using diffusion embedding. And what this gives us is basically a set of gradients, or the equivalent of PCA components, in which all parcels of the surface are now depicted in accordance to their similarity in functional connectivity profile. And when we look at this first principal gradient, then we can see that the areas here of the gradient are embedded or anchored between heteromodal areas, such as regions of the default mode network. And on the other end of the gradient is anchored by unimodal areas, such as M1, S1, V1, A1. So basically, this gradient shows us some form of organization principle that goes from unimodal to heteromodal areas. And certainly the gradient is quite similar in both hemispheres, because both hemispheres have visual areas, motor areas at mostly exactly the same point in geometrical distance. However, there are some slight differences. And to this day, it's not really clear what these differences in the hemispheric architecture of the gradient actually mean for functioning. So González-Alem and colleagues investigated this question by, first of all, getting over 175 volunteers to participate in MRI scans, where they got, on the one hand, resting state functional connectivity, on the other hand, some semantic tasks or non-semantic tasks, in order to then relate the gradient or differences in the principal gradient with these tasks. So they got the semantic tasks, they got the Ravens matrix, which is a visual judgment task or intelligence measure, digit span, as well as perceptual comparison or choice task. They computed the gradient for parcels derived from the Schaefer atlas. And if we now jump here to figure 2 or figure 3, you can actually see a similar depiction of what I've shown you before in the paper of Daniel Margulis. So basically, all of these parcels are arranged in a form that they either tend towards the unimodal end of the gradient or the heteromodal end of the gradient. And if we now compare the two hemispheres here in this first scatter plot, we can see that the gradient values nicely align, but it appears as if the left hemisphere, the gradient values in the left hemisphere appear a bit more shifted towards the upper end of the gradient, so towards the heteromodal end, whereas the right hemisphere or parcels of the right hemisphere tend to be more located within the lower end of the gradient, meaning the unimodal part of the gradient. So one thing that's always tricky in order to compare the two hemispheres on a local basis, meaning regions or structures such as tracts or other brain units, is that we need to have some form of a valid comparison between left and right. So it needs to make sense. If we, for instance, try to compare geometrical structure, volumetric information, it makes sense to look at geometrically the exact position in the brain or the exact gyres in the brain. But with regards to function, that's a bit tricky. You can do it with, for instance, the Aisha atlas, which is built by looking at similarity of parcels between the left and right hemisphere defined by resting state functional connectivity. But what they did was also quite neat. in the sense that they used the geo network and compared left hemispheric parts of the network and right hemispheric parts of the network. So when we're now looking at the hemispheric differences in the principal gradient values along these 17 geo networks, we can depict the difference here with this color scaling, in which these cooler colors denote areas that are higher in their gradient value on the right hemisphere, meaning more towards the heteromodal end, or areas that are also more towards the heteromodal end, but in the left hemisphere. And when we look at this picture here, we can already see that several areas which we would potentially locate within the default mode network appear to have higher gradient values in the left compared to the right hemisphere, and some limbic structures, and here structures in the temporal pole appear to be at the higher end of the gradient in the right hemisphere compared to the left hemisphere. And statistically, that's completely true. So when we're looking here at this figure on the bottom, we can see that only the limbic A network appears to be closer to the heteromodal end in the right compared to the left hemisphere. But networks such as part of the default mode network, control B network, the other part of the limbic network, dorsal and ventral attention networks, they all seem to be closer at the heteromodal end in the left hemisphere. And why could that be important? Well, as I've told you before at the beginning, they also investigated, or they also acquired some functional data, some performance data. So here we can actually see that the positioning or the relative difference in the gradient in a network, or in the gradient network, gradient value of a network between the two hemispheres is associated with performance in tasks. For instance, here, the control B network shows a positive relationship with semantic performance, meaning on the x-axis, we see worse to better semantic performance. And on the y-axis, we see the relative difference in the gradient values going from right hemisphere advantage to a left hemispheric advantage. So if the control B network is in its gradient value leftward lateralized, meaning the left network is closer to the heteromodal end, then this positively impacts semantic performance. But the reverse is true for the dorsal attention network B, where we see a negative correlation with the performance in the Raven's matrix test, meaning here that if the values are higher in the right hemisphere than the gradient values in the left hemisphere, participants tend to perform better in this task. Can also show for these two networks that they actually have some significant differences in terms of their relative position with other networks when looking at these gradient positions. So for instance, in the dorsal, the distance to the dorsal attention network, or the distance between the dorsal attention network and the visual central network, visual peripheral network, somatomotor network, and the other part of the somatomotor network is always bigger in the left hemisphere than it is in the right hemisphere. And similarly, when looking here at this upper part, when we compare the distance between the control B network to either parts of the default mode network, we can see that the distance is smaller in the left hemisphere than it is in the right hemisphere. Lastly, they also try to investigate to what extent this actually factors in with let me have a look here with the functional working memory load. So is there a difference between the hemispheres and between the networks in semantic control when we manipulate working memory? And in order to do so, they used another fMRI data set, which was published by Gao et al. 2021. And they basically just used an ANOVA here. So when looking at this, the paper of Gao basically had included the possibility to change either the task, which means the difficulty of the task, so that semantic associations are easier to make or more difficult. And they looked at the interaction and the main effect of hemisphere and task for the control B network and the dorsal attention network. And here we can see that although both networks show a main effect of hemisphere, they don't show an effect of task, but the control B network shows an interaction between hemisphere and task, meaning that it is indeed lateralized, or that the effect of the task appears to be affecting the laterality of the hemispheres. So just to sum up, this paper basically is the first one to investigate the positioning of the networks in the functional gradient and relate it to function. I'd really like the paper because I really like to see more about how these minor differences in the gradient across the two hemispheres can actually impact functioning. And it would be great to basically see some follow-ups with other cognitive functions, with language, and just more about the general organization principles of the two hemispheres. With that, I think I just conclude my presentation and open the floor for questions.
Thank you, Patrick. Any
You're
questions? No? It was a very clear presentation, I have to say.
Thanks a lot. I mean, it's still kind of a tricky paper, I think, or a tricky topic, because at least for me personally, it's like I tend to think I got a grasp what this gradient means, but I'm not sure if my understanding is really as high as it should be for this. But yeah, we've got some.
I hear you. I struggle with the gradients as well sometimes. Ladies first, Leah.
Hi.
Hi.
So I would like to ask you, your opinion, which is about you the most novel aspect of this paper in the gradient field?
Well, it is, I think, the second paper, at least that comes to my memory, that actually investigates hemispheric differences in the principal gradient and relates it this time to function. So there was another paper, I can't remember from whom, so sorry for that, but that basically shows sex differences in the extent of the function of the functional gradient between the left and right hemisphere. But I can't remember whether or not they also included some functional aspects. So it's the tricky thing is basically when looking here at the left hemisphere and right hemisphere, it looks so similar, right? So why should there be quite an effect of hemispheres? And I think the similarity here has demotivated some people, most likely, to look into hemispheric differences of the gradient. Whereas I think it's really an interesting topic. It's just understudied, in my opinion, at the moment. This is why I'm highlighting this paper.
Yeah, that's true.
Of course, you think asymmetry is an interesting topic. There might be a slight bias here, for those of you who don't know.
I do admit there might be a slight or even a bigger bias. Yeah, but yes.
I have to say that also these heteromodal pictures remind me about the picture that we saw in the CNS talk last week, where there were the multifunctionality of each region. So it seems there is a trap.
Yeah.
Thank you.
Thanks.
Michelle.
Yeah, I have two questions. First, thank you, Patrick. That was great.
Thanks.
So my first question is regarding, like, because the gradient is calculated in the MNI space and at the group level. Mm-hmm. And to do that, you need to stretch many brains. And we know, like, the variability between the right and the left hemisphere is not exactly the same. There are, like, some systematic mistakes. So, I kind of wonder how this could have impacted some of the measure of asymmetry of the gradients. It's
obviously a good question. I can't really answer it fully because, so the thing is, they use the geo networks, right, to compare left and right, or to make a level playing field for the left and right hemisphere in order to compare it. And I'm not sure to what extent the geo networks themselves are biased towards either hemisphere based on the MNI, because I don't remember how the geo atlas was built. So that's why I have difficulties answering this question. Was it built on the asymmetric MNI template or on symmetrical MNI template? I don't know.
I don't remember either. But the reason why I ask this question is when you look at the correlation with the behavior, which are significant, you have you have a lot of noise. And I always wonder whether this is because of, like, fMRI is really noisy, and we know that, and that would be because of that, or is it because we've been stretching those brains? Because when we started working in the native space of brains with diffusion, we found, like, right away those, like, beautiful correlations with behavior. So I kind of wonder whether putting everything, forcing, like, brains into a stereotaxic space can, destroy inter-individual variability and then hide out those beautiful behavioral or cognitive correlations. Yeah. And that's why I asked the question, really.
But I mean, you're right? This is basically the issue. We don't even know who to blame, right? We don't know if it's because of these differences in stretching, basically this asymmetry already between the realignment of the hemisphere that could obviously affect our measures. It could just be fMRI is too noisy, or it could be that the variance shown here between participants is just so high because potentially the effect is just not as, let's say, clear-cut and innate as it could be. So it might not be the most important effect for, or the most important correlate of semantic performance, right?
Yeah.
And it's difficult to entangle this. More research, I guess.
More research.
Always the answer. If I may jump in, Valentina, I saw you raise your hand, but my question was very similar to that. So you showed that the gradient is actually pretty much the same in the left and the right hemisphere. If you go back to the figure before, that one, yes.
Yeah.
But we know that there's anatomical differences. So how would you explain that despite knowing that the structure of the brain is different, the gradient, the functional gradient may still look similar between the left and the right?
Well, albeit function and structure are certainly related, we know that functional connectivity does not equals structural connectivity, right? So I mean, this has already famously been shown by Gracious et al. 2009. I think it was also PNAS, where they investigated nodes of the default mode network, both structurally and functionally, and showed basically that the parietal nodes were statistically, functionally correlated with the frontal, but obviously there's no direct connection between them. So how comes that? It's basically potentially mediator effect, who knows? But what I'm trying to say here is that in order to answer this, we would need to get a better understanding of the structural variance that actually determines differences in the functional gradient. And there's some research on that, totally. For instance, I think there was a beautiful review by Julia Hundenberg, who just summarized some similarities of effects. For instance, the myelin maps gained from the T1, T2 contrast look quite alike to the principal gradient. And I think there are some other studies that also highlight some similarities in the extent of expansion, for instance, with the principal gradient. But we really need to boil down like how structure relates to the gradient. I mean, Michelle, you and I, we've tried to do it with regards to the corpus callosum, and where we basically transformed the principal gradient onto the corpus callosum in order to highlight which areas of the mid segment of the corpus callosum are related to more heteromodal or unimodal processing. But I think like more studies like that need to come to be, basically. We need more studies that really look into the structural determinants of the functional gradient. And also then obviously on individual differences in the gradient.
I agree. Thank you. Valentina.
Hi, Patrick. Thanks for the presentation. Yeah, I was wondering, so the authors present two examples related to the functional differences in laterality between the two hemispheres. And the example that you showed, it's heteromodal tasks. And I was wondering whether they mention the differences in the unimodal aspects?
So they got one unimodal or more unimodal task, I would argue. I think this was the perception, this perceptual judgment task, where a participant need to, as quickly as possible, find the target. Basically, this is the target, this is the search stimuli, and you need to judge which one of the search stimuli are more similar or identical to the target. But I haven't seen if they did a correlation to that or reported it. So that's not saying that they didn't do it. That's saying that I haven't seen this correlation or the reported null correlation. So I would have guessed that if they found an effect like that, they would have reported it more clearly so that even me would have seen it after quickly reading through the paper. So can't really answer, but I think in general, it's an interesting question. Given that apparently the right hemisphere or nodes within the right hemisphere, parcels within the right hemisphere, and thus networks in the right hemisphere tend to be more closely positioned towards the more unimodal end. So, I mean, one could, for instance, look into other tasks such as auditory perception tasks, dichotic listening, something like that, to see to what extent this potentially has impact also on some unimodal tasks and functions. Yes.
Yeah, I guess, and it also means that you must have a really complete battery of tasks when to mix the modality and content of the task. For instance, they show here the example of semantic performance, and I would say, I mean, it's expected as a result, no, that we see a better performance with the gradient of the left hemisphere, and I was wondering if there is another task that they tested, like, I don't know, theory of mind, which is many studies found left or lateralized, whether this is true also for, I mean, other tasks that do not involve the verbal domain.
Yeah.
But thank you for your answer.
Thanks for the question.
You guys are so polite. Michelle, is that a new raised hand or an old one? A new one. Here we go.
Yeah, I see. It's always like a super interesting question. And I was with Daniel Margules last week, so we spoke about that. So one of the main issues with the gradient is like it's really difficult to extract it at the individual level. And, you know, it doesn't look so great. But the good news is with the function nectome, we tried it. Actually, you can now. And that's so maybe we'll be able to disentangle those two. So if you create a map of structural distortion and a map of the functional gradient in the MNI space, you can actually regress that one from the other. I think FSL give you this possibility. You can have like a 3D regresses to your analysis. So then we have time to take care of all these additional questions that we would like to explore.
That one fine day when we have time.
Yeah. But that's really cool that you mentioned that. Oh,
sorry.
Yeah,
no, sorry. Just here we go.
Did you had enough of my live face? Just wanted the picture. Is it that?
I wanted to stop the sharing, not your video. Didn't even know I could stop your video.
I didn't know either. Yeah. No, but as I said, Michelle, so it would be really cool. Probably we can talk about how to use the functional nectome at some point for that. But I think, as Steffi already said, if we find the time, there are other things at the moment, unfortunately.
One day, just gonna ninja those projects.
Yeah.
Right. Any more questions? No? Are we getting a music interval to go out? Great. Thank you all for joining us this Monday morning, bright and early, and we hope to see you again next week. Are there any volunteers already? That's what we're going to have for an hour next week if no one is presenting a paper.
Otherwise, Hervé can just make some music for us the entire session.
Oh, we can have a dog also. Oh, I saw
Yeah,
it.
he's not
Want to
supposed
say
to.
hi to others.
He's the scene's mascot, but he's not supposed to get involved here. But I don't hear him what he's doing. That's the problem. So he sometimes surprises me. Anyways, not the point. Let me know if you find a paper over the week and you want to present it. Otherwise, we have Hervé play music for us next week. Have an exciting week in science, and we see you Monday morning. Bye.
Bye.